In this lecture now we'll be starting with the DC series motor. So as compared to the DC shunt motor, the main difference of a DC series motor is that your series winding, your field winding is in series with the armature winding. So this here can be used to represent the equivalent circuit of a DC series motor. If Vt is your terminal voltage applied to the motor, Rf represents the field resistance, Ra represents the armature resistance, the resistance of the armature winding. So the field windings and the armature windings, they will be placed in series in case of a DC motor. This L here represents the total armature inductance. As we have been seeing that the inductance basically is ignored in a DC motor because of the simple fact that the inductance of the windings will actually, as the DC as steady state will be achieved in the system, DC current will be flowing through the system and the inductor will be shorted out. So we can actually neglect the inductance in the DC motor. And EA represents the internal generator voltage of the DC motor, or you can also say this is actually the back EMF of the motor. So the main difference here being that Vt is equal to Ia into Rf plus Ra plus Ea. Fine. Our terminal voltage will be given by this relationship, or we can also write from here Ia is equal to Vt minus Ea divided by Rf plus Ra. As far as the DC series motor goes, since the field winding here is in series with the armature winding, so the same amount of current is flowing through the armature as well as through the field windings. That means the armature current is flowing in this case through the field windings as well. So whatever the flux is being produced by the field windings, fine. So flux that's actually being produced by the field windings, in this case the flux will not be proportional to If. So since there is no quantity like If here, flux in this case is simply proportional to the armature current. So greater the armature current, greater will be the flux produced in the field windings. Lesser the armature current, lesser will be the flux produced by the field windings. We already know that torque induced in the machine is equal to K phi Ia. Now what we are saying is, we are saying phi is proportional to Ia, or we can write this as phi is equal to CIA, where C is any constant of proportionality. Therefore, what will torque induced be equal to? Torque induced is equal to, therefore, Kc Ia square. So once you substitute phi here, you see that torque induced in the DC series motor is equal to Kc Ia square. That means torque induced is proportional to the square of the armature current. So what does this basically imply? This means that the DC in a DC series motor, the torque that will be produced will be more as per the series motor will have more torque as compared to a DC shunt motor for the same value of armature current flowing through the armature circuitry. A DC series motor will be producing more torque as compared to a DC shunt motor. So, accordingly, a DC series motor is used for those applications where high torque demands are a requirement. As in case of a number of traction systems, we prefer to use DC series motors, or in case of cars or elevators, any traction devices that you have, locomotives, there we prefer to use series motor because of the simple fact that induced torque or the torque produced in a DC series motor is more per ampere current flowing through the series in the DC machine. So we have these applications like traction devices, we have locomotives, we have elevators. So where high torque is a requirement, and therefore a DC series motor is a preferable choice rather than a DC shunt motor. And what else can we deduce in a DC series motor? Now, since flux in a DC motor is proportional to armature current, so as the load on a system will increase, if we increase the load on a DC series motor, the drawn current from the current that will be drawn by the system will be more. That means armature current IA will rise. So if IA will rise, that means in a DC series motor the flux will also increase. Now this increase in flux, fine, so increase in flux, we have already seen what happens with increase in flux. The speed of the motor will decrease. So since there is a direct relationship between the armature current and flux here, we'll be seeing in case of a DC series motor there will be a drooping characteristics. There will be the speed versus torque profile will be much more. There will be a significant droop there as compared to a DC shunt motor. Now let's see the terminal characteristics of a DC series motor. That's the speed torque characteristics. To understand this better, we'll first of all derive the speed equation of a DC series motor. We know now Vt is equal to EA plus IA RA plus RF. Fine. We saw that torque induced is equal to IA Kc into IA Kc IA, where C is a constant of proportionality. From this Kc IA square rather, sorry, and from here we can say IA is therefore equal to what? Torque induced divided by Kc under root of this. Substituting the value of IA here, we'll be getting Vt is equal to EA plus under root of torque induced by Kc Ra plus Rf. Now instead of writing Ea, what we can do is we can write K phi omega. Fine, we know this relationship. We'll try to get rid of phi. Phi is equal to C times Ia. We have already written it here. Phi is equal to C Ia. But what is Ia? We just found out that Ia is equal to torque induced by Kc under root of torque induced divided by Kc, or in other words we can therefore write phi is equal to torque induced into C divided by K. We have C and you have under root of C at the bottom. It's not subscript of this is K into C. Fine. So therefore phi is equal to torque induced into C divided by K. So we can substitute this here. K, instead of phi you can write now torque induced into C divided by K, and then you have omega plus under root of torque induced divided by K into Ra plus Rf. Again this is K divided by under root of K, so you can simply write this as torque induced into C into K divided by into omega. This is under root into omega plus under root of torque induced divided by K into Ra plus Rf. Now we actually want to find out omega from here. Therefore omega is equal to Vt divided by torque induced into K into C. This is Vt equal to which this whole thing, so Vt divided by torque induced into C into K minus this whole thing divided by torque induced into C into K. Minus torque induced divided by K into Ra plus Rf divided by torque induced into K into C. Fine. So you can also finally write this as torque induced into K into C minus torque induced cancels out here. You have at the top Ra plus Rf divided by under root of C. K is outside. This is actually K into C, so this becomes Kc. Fine. This is K into C. So this is our equation for speed in case of a DC series motor. Now using this equation you can plot omega with respect to the torque induced in the motor. Fine. So once you plot this equation, so as at torque induced equal to this characteristic will start actually from here, and you will see it will have a sharp drooping characteristics, and the motor will the speed will fall very quickly with respect to the torque of the with respect to increasing torque of the motor. Fine. So we are starting from this point instead of starting from here, because you can see if torque induced is equal to 0, if we substitute torque induced equal to 0 here, this term will become infinity. That means speed will become infinite. For a series motor at torque induced equal to 0, the speed is infinity. So what does that mean? That means the motor will be seriously damaged if we are actually unloading the system completely. There is no sort of load attached to the DC series motor. It's freely running. In that case, the induced torque will be 0. Since the load torque is 0, naturally the system will balance out at, and the torque induced will also be equal to 0. So omega will become infinite. That means even if it is not infinity, even if you can see that it is close to 0, even if torque induced is close to 0, omega will be very large. So that sort of condition needs to be avoided. So a DC series motor, this is very important here. DC series motor never run it unloaded. Fine. Practically, the induced torque will never be equal to exactly 0, because the mechanical bearings of the machine to overcome the core and friction losses, some amount of induced torque is always there, but that induced torque will not be sufficient enough, even if it is only 0.01 of a Newton meter. This value here will be significantly very high. This particular value that we are suggesting here, this particular value will be enough to cause damage to a motor. If the system is completely unloaded, theoretically speaking, if there are no losses, ideally induced torque will be 0, therefore the speed will be infinite. That will cause damage to the DC series motor. Practically, there are the mechanical bearings, there are friction losses, stray losses, etc. Therefore some amount of torque induced is always generated, but if that will be very small, of the order of, if I can say it, maybe even if it's of the order of 0.01, this value will be very large. So starting torque of the motor will be significantly much larger as compared to a shunt motor, particularly if the motor is run unloaded. That can actually cause a significant damage to the motor. So never run a DC series motor without a load. Always connect a load before running a DC series motor. Use some sort of brake mechanism, or else to make sure that there is a considerable value of induced torque in the machine that will not cause harm to the DC series motor. Otherwise else, you can see as the induced torque increases, the speed of the motor drastically decreases, and this is an important This behavior is actually very important for traction devices, and where you actually have a very high starting torque, and we can basically maintain a high torque at in case of DC series motors. So this is the speed torque characteristics. Now moving on, let's do a numerical on this. We have been given a series motor, a 250 volt DC series motor, whose combined RA plus RF is equal to 0.08 ohms. The series field consists of 25 turns per pole, and the magnetization curve of this system has been given to me and given to us. Fine. Magnetization curve, almost similar to what we have done in the last question. So whatever values need to be checked from here, I will be giving you those values later on. Series field consists of 25 turns per pole. So find the speed and induced torque of this motor for when its armature current is 50 amperes. So we have to find speed and induced torque for IA equal to 50 amperes. So what do we have here? We know EA is equal to, for a DC series motor, VT is equal to EA plus IA RA plus RS. Here we have been given a combined resistance of 0.08 ohms. So therefore EA is equal to VT minus IA RA plus RS. So EA is equal to VT is 250 volts minus EA is equal to VT minus IA RA plus RF. Therefore ET is equal to 250 minus IA has been given to us 50, RA plus RF is being given to us combined is 0.08 ohms. So this total becomes 246 volts. So we have been given a magnetization curve, and this magnetization curve is showing us EA with respect to MMF. Fine. And first of all, let's calculate the MMF of this machine. MMF, what will be the MMF of this machine? We know MMF is equal to N into I, where N is the number of turns of the coils. Since we have 25 turns, so 25 into 50, that is equal to 1250 ampere turns. So this is the MMF value. From the magnetization curve, now we need to actually find out the EA generated in this machine to get the speed rating, to get the value, the speed of the motor. So we have been given an MMF rating of, so we have been given here 1000, 2000, from here it is somewhere around 50, this is 100 extra, this is 1000, this is 2000, so corresponding to 1250, that will be somewhere here. We need to see what is the value from this. So from the magnetization curve that I'll be giving to you separately, we get EA of 80 volts from magnetization curve corresponding to MMF of 1250 ampere turns. EA is equal to, so approximately this is coming out to be equal to 80 volts. So EA is equal to 80 volts. We have derived last time an equation where we know EA is proportional to the speed of the motor. Fine. Therefore we can say EA1 divided by EA2 is equal to N1 divided by N2. So N1 is voltage corresponding to EA1 and N2 is speed corresponding to voltage EA2. Fine. N1 is the speed corresponding to voltage EA1, and in the question itself, one thing was again given: the rated speed of this machine is 1200 RPM. 1200 RPM. So EA1 is 246 volts, EA2 is 80 volts, N1 is 1200 RPM, N2 is what we need to find out in this machine. So from this equation, N2 is equal to correction here. We have been given N2 equal to 1200 RPMs, and we need to find out N1. We need to find out the actual speed corresponding to the current 50 amperes, corresponding to which the voltage was 246 volts. Fine. So N1 we have to find out in this case. N1 will be equal to 246 into 1200 divided by 80. So that's equal to 3690 RPM, and corresponding to this we have to also find out the induced torque of the machine. Now we know that the induced torque of a machine is equal to EAIA divided by omega, P divided by omega, EAIA divided by omega. EA is equal to 246 volts into 50 divided by omega, where omega is 3690 into 2 pi divided by 60. So this comes out to be equal to 31.8 Newton meter. So the thing here is we need to find out this curve has been given for a rated speed of 1200 RPMs. It's EA versus MMF plot. The only thing here is significant here is that we need to find out EA corresponding to the MMF value generated in the machine. So let me give you this magnetization curve first of all here. So this is the MMF curve that I was talking about. This has been given to us. So here you can see it is MMF versus this here is an MMF versus voltage plot. So corresponding to 1250 we need to basically find out what is the value of induced voltage. So that's equal to 60 volts, and this is for a rating of 1200 RPMs. So corresponding to 1200 RPMs we have found out the voltage to be equal to 80 volts. We need to find out the speed corresponding to a voltage of 246 volts. That is what we have calculated using this equation. Corresponding to 1200 for a rated machine of 1200 RPMs, for a MMF of 1250 volts, the internal generator voltage should be 80 volts, but our internal generator voltage is coming out to be 246 volts. So we need to find out what is the actual value of speed. We can also roughly estimate the value of speed from this magnetization curve as well. At 246 volts, what should be the value of the it may give us actually higher speed because of the saturation effect. To find out the actual speed, we will use the equation that we have derived, and from that we are seeing that the actual speed is equal to 3690 RPM, somewhere around that range. Fine. So this is about DC series motors, the torque speed characteristics. We need to study the speed control of DC series motor. That we'll do in the next session.